Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be starting a new module where basically we'll be looking at the applications of the notion of derivatives that we developed in the previous module. Let me not recall anything from the last time and immediately get into this new module. These are the two problems. And now let us quickly finish this lecture. This is going to be a short lecture. So let f be a function defined on a set S and let x naught be a point in S. We say that f has a local maximum at x naught if there is a neighborhood u of x naught such that whenever we choose a point in u as well as in the domain of f, we see that f of x is at most fx naught. So let's see an example. So suppose my function is like this, meaning this is the graph of the function, and let's say this is x naught. Let me redraw. Suppose it is like this. So as we can see, the figure as it is trying to say is that if you take a small neighborhood around x naught, then the graph of the function above that neighborhood looks like this. So if you take any point in this neighborhood, the value that you get corresponding to that point is at most the value that you get for x naught. So that is a local maxima, this point. And this point, for instance, is not a local maximum, because if you take any neighborhood you want, no matter how small, there are always points which beat the value that f takes on x naught. So this is a local maxima. Okay, let me remove this because it's ugly. So it's a very simple concept. And similarly, we can define local minima. That I leave to you, and these two definitions together can be put together to form a single word, which is local extrema. So a local extrema, or rather we say that f has a local extrema or extremum at x naught if it has a local minimum or a local maximum at x naught. Okay. And now finally we define global maxima. So we say f has a global maximum at x naught if fx is at most fx naught for all x in the domain. Self-explanatory terminology. Similarly, we can define global minima and global extremum Okay, and let us quickly take a very simple example. Let's suppose f is this function, which takes x to x. Then f does not have a local extremum at any point. No matter what point you take in the domain, there is a neighborhood such that if you move towards the left of that point in that neighborhood, you will be decreasing, and if you move towards the right of that neighborhood, you will be increasing. So it is neither local minimum nor local maximum. So it is not necessary for a function to possess local or global extremum or any such thing, but in special cases they do, and we've already seen such things. So if f a to r is a continuous function, and a is compact, in particular if a is a closed interval, then f has a global maximum as well as a global minimum. So we saw this when we were discussing compactness. Okay. So now what does this have to do with derivatives? Here is the lemma. So let f be a function on an interval So we have a function defined on an interval I, and fix a point in this interval, and assume that f has a local minima or local minimum at x naught. Then we'll show two things. If f is the right differentiable at x naught, then the right derivative of f at x naught is non-negative. And two, if f is left differentiable at x naught, then the left derivative is non-positive. And one should understand this first in terms of pictures. So the simplest example would be, let's say, something like this. So this is the graph of f. And here we have a local minimum. So then, as you can see, well, in this picture the derivative is actually 0 because, well, so suppose your function was differentiable at x naught and x naught was an interior point, then what would we have? We would have that the right derivative is non-negative, the left derivative is non-positive, but if f is differentiable, then these two things are equal, so then both of them have to be 0. So the picture that I've drawn here, you have a differentiable function, and hence at a local extrema, at a local minima, the derivative should be 0. So just to imagine this in terms of pictures and you'll see what's happening. But anyway, the proof is also just a one-liner, although the theorem, in fact, this is one of those cases where the theorem is longer than the proof. So since this is a local minimum, or since f has a local minimum at x naught, there is delta greater than 0 such that whenever you pick x in a right neighborhood, right delta neighborhood of x naught, then what happens? Okay, so let me write it. So then such that fx exceeds fx naught whenever x belongs to this. In fact, I could have written x naught minus delta, x naught plus delta also, but let me just write this because this is also true. So this implies, therefore, this guy is non-negative for all x in this open interval, right? Because this is also positive and this is non-negative whenever you have x in this open interval, and therefore the limit also is non-negative. Since we are assuming that the function is right differentiable at x naught, this limit exists, and by the above line this has to be non-negative. So that's it. That implies that the right derivative is non-negative, and similarly, exactly similarly, you can do the left derivative part. So that's it. That's the proof. So just one more lemma and we'll be done. Let me do it here. So this time again we have a function. Let f be a function defined on an interval. Interval I. Let x naught in I be such that, so let x naught be I in the interior of I, and f, and assume that f is differentiable at x naught. So the conclusion is, if f has a local extrema at x naught, then the derivative vanishes. And this is what I said while I was arguing this, so I won't be repeating the proof. This is just an exercise now, and let me finish with an example. So what we have proven here is that if you have a local extremum at a point in the interior of the domain where the function is differentiable, then the derivative must vanish, but the converse may not be true. So it is not necessary that if the derivative vanishes at an interior, so let me not write the full sentence, but if this is the case, then x naught is a local extrema. This is not necessary because you take the case where you have this function, the cube function, then this is 0, but 0 is not a local extrema, because if you take the graph of the function, it looks something like this. This is the origin. So this is neither a local maxima nor a local minima, because as you go towards the right, it is increasing, and go towards the left, it is decreasing. So just one direction is true, as shown by this. So that's it. There is nothing much going on. Alright, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.